the geometric transformations are really the start of Unit 6, and they're actually kind of a simpler version of the linear transformations that we did before, because the linear transformations, you can go to other dimensions like r cubed and so on. Here we start at r squared and we go to r squared. So geometrically, we're always staying in 2D to 2D, or I suppose 3D to 3D. I haven't seen those. We're just working with 2D to 2D this chapter. With 2D to 2D, then you can kind of look at some of the basic transformations like stretches, shrinks, reflections, projecting onto a line, things like that. So what I'm going to start with is just reviewing what you're actually doing to the points. You're taking a point, P of xy, and you're changing it somehow to Px prime y prime. Now what's cool about this is that this new x prime is just going to be some manipulation of x and y. The new y prime is going to be some manipulation of xy. So what are you manipulating? Well, you're going to manipulate it with different constants, a, b, c, and d. And as we know, with anything combination-wise, you could write this as matrices x prime, y prime is something times xy using the rows by columns approach. Ax plus by will be ax plus by. And then the next one will be cx plus dy. So with that matrix, you have A, B, C, D is your transformation matrix A. XY is what you started with, and AB is your transformation matrix to make it x prime, y prime. They had a nice example of how you could actually move points and change equations. So under T, find the image of this point 3, 2. So x prime, y prime. All they did is they said this is x, goes in here. This is y, goes in there. And so 3 times 3 minus 2 is your 7. But that's just the x prime. You need to do something, the other formula, x plus y, 3 plus 2, to get you the y prime. So that's what they did here. Simple enough. Now the equation, a little different here. They wrote this as the AX matrices, 3, negative 1, 1, 1, and XY. And what they wanted to do is they wanted to find the transformed equation. So how do you think they got rid of this to solve for XY? Well, they did the inverse. And that's where the inverse comes from, and that's why you go 3 minus negative 1 is 4, 1/4. Switch the 1 and 3's, oppositize 1 and negative 1. I just made that up. And then you get the equation x equal to 1/4 x prime plus 1/4 y prime. And y will be equal to negative 1/4 x prime plus 3/4 y prime. Okay, so now you have those two equations, and then they wanted you to find the image of that transformation through that equation. So all they did is they said that y equals 2x minus 1. You've got your x, you've got your y. Plug those in and solve algebraically, and that's what they did here. And they ended up with 3x minus 2y equals 4 is your new transformed image of that line after you moved it through this transformation. But that's only one transformation. We're going to look at several transformations that can occur, and the ones that they focus on here are rotations about the origin, which is a good one because if you rotate about the origin, what you're essentially doing is you're anchoring your pivot point at the origin, and then you're pivoting that point pxy to pxy prime. And oftentimes they'll give you an angle to move off of, and so therefore you'll be able to figure that out. Now I want to direct your attention to the formula that's all proven here. I think you can follow it pretty well. It's got some SECO, COSI, and COCO-CC in it. And you can see what they did for x prime, y prime, and how they took the coefficients, cosine theta minus sine theta, and sine theta cosine theta off of the transformed equation to get this A. But I'm not going to prove that. What I want you to notice is what the determinant is of this. Cosine squared theta minus a negative sine squared theta, which is equal to 1. This is a unique property of this transformation that allows you to identify a rotation transformation. Okay? And if you take the determinant and you get 1, it's a rotation transformation. That's what the formula will yield. An example of this would be, let's say you're going to rotate so we might want to find the transformation matrix to rotate about theta equal to, let's keep it simple here. Let's go 2 pi over 3. Well, you take the formula. A is equal to cosine theta, 2 pi over 3, negative sine 2 pi over 3. And you have the sine of 2 pi over 3 and cosine of 2 pi over 3. And then when you put those together and simplify them, you'll just get on the unit circle 2 pi over 3. Cosine will be negative 1/2. Sine of 2 pi over 3 is square root of 3 over 2, but it's going to be negative because of this sign. Sine of 2 pi over 3, square root of 3 over 2, and cosine again is negative 1/2. So this is the transformation matrix. And anytime you want to tell if it's a rotation, just take the cross or the determinant and see if it equals 1. But there's more. There's lots more. We've got a lot other types of transformations we can do. Reflection in a line. So what they mean here, I would say about a line. In other words, we're taking a point and we're reflecting it about a line to be swinging past it like a door, swinging past that point. And they defined it, they did a nice job of proving it, and I just want to give you that formula. And notice that when we do the determinant of this one, you're going to get cosine squared 2 alpha negative minus sine squared 2 alpha, and that's equal to the opposite of cosine squared 2 alpha plus sine squared 2 alpha. And what's that equal to? Negative 1. So if you have this kind of transformation, the line is changed to tangent alpha times x. That's like y equal to mx. M is the slope, x is, of course, any value along that. Notice that the y-intercept is equal to 0 for this transformation. We're going about a line that's going through the origin. We'll look at some other lines later, but for those that go through the origin, this is the transformation that we can do. Okay, working with transformation matrix for reflections, they do some substituting here, show you where if m is the tangent of alpha, they did these nice little transformations for you. So, for example, if you look at cosine 2 alpha, 1 minus m squared over 1 plus m squared, you can see how that turns into cosine 2 alpha, and so on. Those are kind of cool. Okay, and so here's a problem example that I want to go over real quick. This does the rotation using this rotation formula. Just put the angle that it's going counterclockwise to. Now notice that this one's going clockwise, so you just need to go 2 pi minus that to get the clockwise. Excuse me. So if it's going clockwise 2 pi over 3, just remember that this is going to be theta equal to 4 pi over 3 counterclockwise, and you just plug those in and you'll be fine. For the reflection about the line y equals 3x, m, of course, is equal to 3, because y equal mx plus b is 0. And so if we know the slope is 3, we can get these gems by doing the equations that we proved earlier, or that were proved earlier. I didn't prove them, but the cosine 2 alpha was 1 minus m squared, 1 plus m squared. So that you can substitute the 3 in for, and then you'll get negative 4/5 for sine 2 alpha. You can go into those two, and you're going to get 3/5, and that's going to give you that. So then what happens is that once you have these cosine 2 alpha, sine 2 alpha, you can just plug those in, and you get the nice transformation matrix for that line, y equal 3x reflection. That's kind of nice to see an example. Nature transformations, all you have to do is take these and, you know, negative 3/5 x minus 4/5 y, negative 4/5 x plus 3/5 y. Those are the x prime and y prime. And what's cool about that is that now you can take the coefficients to make your transformation matrix. So you have the transformation matrix. But to figure out what it means, all you have to do is do the determinant. Same thing with this example B. Take the determinant. If I get the determinant, I get -1. -1 means a line. This is a y equal to mx reflection. And then for this one, if you take the determinant, you get 1. 1 meant that it was a rotation reflection. Rotation transformation. And they even found the thetas and all that. I'll let you look at those examples, but that's just kind of like what we just did. So that is rotation about theta, which is counterclockwise, and then it's the reflection about the line and how you can use that formula. So it's these two formulas, and you're stuck with them. You're going to have to use them for, hopefully those are in your packets. If they're not, those you would need to know for your rotation and line reflection. This is it for part 1 on geometric transformation.